A lift arrangement shown below comprises an electric motor, a cage, and its counterweight. The counterweight moves vertically downward. That is counterweight. You can see it moving vertically downward. As the cage moves upwards, you can see the cage moving upward, and then this is the electric motor which rotates to cause the movement. The counterweight, the cage and counterweight move at the same constant speed. Let us take note of this word, constant speed. Then we come to the questions. The cage carrying passengers moves vertically upward at a constant speed, covering 60 meters in 2 minutes. The counterweight has a mass of 900 kilograms. The total mass of the cage and passengers is 1,300 kilograms. The electric motor provides the power needed to operate the lift system. Ignore the effects of friction. And then 5.1, calculate the work done by the gravitational force on the cage. Now this is the cage, so let us see to calculate work done by the gravitational force. The formula we have to choose here is the first formula. Work done is equal to the force times the displacement times the cosine of the angle between the force and then the displacement. So if we have to calculate the work done by the gravitational force, then we need to know the magnitude of the gravitational force, then the displacement, and then the cosine or the angle between the displacement and then the gravitational force. So let's check it here. Now we can draw a free body diagram so that we can see things clearly. Now the dot is our cage, and then there's a tension which is the rope up, and then the gravitational force is acting downward, which is Fg. Then the cage, if you remember, moves up, and then we can just go there for you to see. This cage is moving up, and so we have that free body diagram that is showing the direction. The green arrow is showing the direction of the motion or the direction of the displacement. Displacement is up, and then the gravitational force is down, and the angle between them is 180 degrees. That is the angle on a straight line, which is 180 degrees. So we say that work done by the gravitational force on the cage is work done by the weight of the cage, which is Fg. The gravitational force is Fg times the displacement times the cosine of the angle between them, and then we remember that Fg is mg, which is mass times acceleration due to gravity times the displacement times the cosine of the angle, which is this 180, and then the mass of the cage. We can go back and then verify what we have here. The mass of the cage, the total mass of the cage and passengers is 1,300 kilograms. So the mass of the cage is 1,300 kilograms times 9.8 is the gravitational acceleration times 60. 60 is the displacement. Let us go and verify that one also. That is it says that the cage carrying passengers moves vertically upward at a constant speed, covering 60 meters in 2 minutes. So the distance or the displacement is 60 meters up, and then that is 8. and then when we use our calculators, then times the cosine, which is cos 180, and then when we use our calculators to evaluate this, we get negative 764,400 joules. Then we come to the next question, which is 5.1.2. Calculate the work done by the counterweight. Remember, the counterweight is also is using its own weight to do work in this system. So we have to find its weight, or the gravitational force acting on it. And when we go back, we also draw a free body diagram. We see the tension up of the counterweight, and then the weight of the counterweight is also downward. But here the displacement, or the motion of the counterweight, is downward in the same direction as the gravitational force. So what has changed is now the angle between the displacement and then the gravitational force is going to be 0 degrees, because they are in the same direction. And then we say work done by the counterweight is equal to the force exerted by the counterweight, or the weight, the gravitational force, times the displacement times the cosine of the angle between them. And then what is the mass of the counterweight? We can go and verify is 900. We verify that that is the counterweight has a mass of 900 kilograms, so that is correct. And then we substitute 900 kilograms as the mass, which is m, and then 9.8 is the acceleration due to gravity, and then we get the weight, which is a red. Then it also moves downward. Remember, it is moving at constant velocity, so the displacement for the two will be the same, but in different, the cage and then the counterweight will be the same, but in different directions. So this one is also 60 times cos 0, because the displacement, that's a green, and then the gravitational force are in the same direction. And then when we evaluate that with our calculators, we get 529,200 joules. Then we go to the third question, which is 5.2. Calculate the average power required by the motor to operate the lift arrangement in 2 minutes as explained above. Assume that there are no energy losses due to heat and sound. So we assume that there's no loss of energy anywhere, and that means that the work done by the system is equal to the total work done by the system is equal to the work done by the counterweight, and then the work done by the cage, and then the work done by the motor. So here we have to calculate average power, and we are given time, information about time. So what we do is we check the formula sheet for power, and we see that we have power is equal to power average is equal to the force. This one is an applied force times the constant velocity. We're not given the constant speed. We also don't know the applied force of the motor, but we are given time, so which makes this formula an appropriate one. Now we say power is equal to the work done by the motor divided by the time taken. Since we know the time information, we can calculate the work done by the motor, and then when we divide that by the time, we get the average power of the motor. So that is it. And we go and then say power developed by the motor is equal to work done by the motor divided by time. And then to calculate the work done by the motor, let's remember that this system was moving at a constant velocity, and the total work or the net work is equal to 0. So we say that the work done, the total work, is equal to work done by the cage plus work done by the counterweight plus work done by the motor. And then when we substitute the 0, remember when the system is moving at constant velocity, the change in kinetic energy is 0, acceleration is 0, net force is 0, and then net work is also 0. So we substitute that, and then work done by the cage is what we found in 5.1.1. We substitute that one, plus work done by the counterweight is what we found in 5.2 with 5.1.2, plus work done by the motor, which is the only unknown variable. And then when we use our calculators, we add this one, we say this negative this plus this, we have this. Work done by the motor is equal to 235,200. And then when we substitute that into the power formula, we get power is equal to work done by the motor, which is 235,200 divided by the time. Remember, when we use this formula, time should be in seconds, but what is the unit of time? We're given time in minutes, 2 minutes, so we have to convert 2 minutes to 2 seconds, and then that gives us work done by the motor, 235,200 divided by 2 minutes times 60 seconds. And then when we use our calculators, we get the work done by the power of the motor, or the average power of the motor, to be 1,960 watts.